Thanks. So welcome everyone. Yeah, sorry again. I think we are going to run out of food. So next week we'll order more. But it's my great pleasure to introduce Kostas. So thank you very much, Kostas, for agreeing to do the talk. Actually, I was just telling Kostas that we have been in this department for 25 years, but I have never really listened to him give a talk. So this is going to be a great opportunity. So Kostas is a world leader in computer vision, and these days, as we all know, deep learning is an integral part of that. And today is going to tell us about equivariance in deep learning.
All right, thank you very much, Rajiv. Thank you everybody for joining. This is a joint work in alphabetical order by Christine Evangelos, my collaborator, Edgar Dobrivan from Wharton, Carlos, who is now at Google Research, Christine is at Princeton, Jacques Lay here, Amit, 15 years graduate alum, and Stefanos and Yin Shuang, current PhD students. So please interrupt me. I mean, there is a lot of material and some of them is really superficial. So interrupt me if to explain, so that I explain more. So symmetry means equal measure in Greek. And it really means equal measure under transformations. So whether it is like a finite rotation, like here, or a scaling, snowflakes, like webs, and the wings of the peacock. And it has been shown by experiments in the monkey's brain about 25 years ago in Max Planck by Nikos Logothetis, and it's also now textbook material, that if you show to a monkey an object that is not from its environment, like a paper clip, and you show it in different orientations, you're going to find neurons. These are firing rates over time. You're going to find neurons which react to specific viewpoints in 3D, so in the full three-dimensional rotation space. And if you take the vector over all rotation or a spherical representation of this vector, then this is what we call an equivariant representation, because if the object moves, then correspondingly the whole vector of neuron firing rates will move. And
what does training on only 3 or 4 views mean?
Oh yeah, this is also, I forgot to say that. This is very important. This means that the monkey was shown only 3 or 4 views of the paper clip and not all of them. Okay, and this is to emphasize that the monkey was not exposed to a full data augmentation. Good point. And then later, Jim DeCarlo with Nicole Rust, who is professor now here in psychology, they made an experiment with other objects, also unknown to the natural environment of the monkey, like cars and airplanes, in an area a little farther down in the brain of the monkey. And they measured the firing rates at 40 electrodes. And then they saw that if they take just a linear SVM, as we say these days, layer, then a linear classifier, then you could really predict by just seeing the firing rates whether the monkey would see a car or an airplane independent of orientation, scale, and also they have experiments on background. But for sure, with respect to the orientation and scale, this means that during what is called the ventral stream, the visual pathway, while at the beginning the cars and the airplanes are quite actually distributed non-linearly with respect to their representations, that the more we go to the back of our head, the more they are actually separated beautifully. And the conjecture is that this is due to this equivariant representation that we have this view selectivity in the neurons. Yes.
Linear, the representation is in terms of the activation of the neuron.
Yes, these are 40 electrodes firing rates. So you have without having visual input, just from the electrodes, that you can predict what the monkey is seeing. So
Sorry, just
yeah,
I don't understand biology very well. The
sorry.
picture is supposed to represent that there's like a part of the brain closer to the eyes or something where it's not linear, but then as
Yeah.
you measure further back, it's
It becomes you can separate them linearly. Now let's go to a few definitions. So everybody who has taken a class in signals and systems knows that the convolution and the linear shift invariance, like LSI, as you say in electrical engineering, are really equivalent things. So, which means that if you apply a convolutional filter, which is a translation convolution with a classical definition of translation, then the result, if you translate the input, the result inside this window remains exactly the same. However, if you apply the same translational filter, like the mask you have learned in the basic image processing class, and you rotate the input, then you see that the content of the window does not remain the same and changes together with the rotation. So more general, okay. Okay, thank you. More general, if we define an equivariant map as of features, phi, which you can imagine as a layer of your network. You can define a map as equivariant if it really commutes with the group action in the picture. And this equivariant map phi can be, for example, convert this is usually a sequence of layers that achieve the semantic segmentation. Here the color is really of every pixel has a vector like of 40 classes with we can say much like a softmax output. And the equivariant means that if we rotate the input, and forget now the result, if we rotate the input, then I can directly predict what will be the result of exactly the same actually layers without even probably running the layers. This means that I don't have to provide additional, if you want, I want the network to, let me write. So the question, if I want the network to generalize to transformed input, lambda z, I don't really have to provide the network with this as samples. The reason we were gonna use several notations for, so z is the transformation. The reason we don't write z here is because the lambda z is the warping operator on the image. It's not really the actual rotation times xy. So this is, you should look at it as warping the whole image. If you take the whole image as a huge vector, this is like a linear matrix that maps every pixel to something else. And we use the prime here because the image might be have RGB, but here maybe it has 40 values, like the logics of corresponding to 40 classes for every pixel here. Is this definition clear? Yeah.
You comes from the group.
Sorry?
You comes from a group and lambda prime is some function of lambda.
Lambda prime is just something that operates on like a whole number of channels. That's it.
If you tell me lambda G, then there's some computation I can do to figure out what is lambda G prime.
Purely deterministic thing. So, and equivariance matters for many things. One is, for example, in this panoramic segmentation for with respect to three-dimensional rotation, if we don't apply, if we don't have an equivariant network, then this is really the result we get when it rotates. If everything becomes scrambled. And this is from a paper called Strike with a Pose, where actually it is trained with adversarial examples. And you see, I mean, many of them are non-realistic, obviously, like this one. But in this case, school bus is recognized as snowplow and fire truck as bobsled. Now, this is a very serious problem, but most of the people do not apply the results that we are gonna describe here. The reason is that there's a very easy way to achieve some kind of approximate equivariance by just taking your whole data set, and this everybody, I mean, raise your hand if you have done it in any network, right? All of you. Probably, you take your input images, you rotate them, you translate them, you crop them, you scale them, and you add them as samples. So you multiply your input data set by a factor of 100, and these become part of the input distribution. So rotated sample is not anymore out of distribution.
This is also what you did with the monkey, though, right? It's like you showed only 3 to 4 views.
Yeah,
So that
this is not what was done with a monkey, and there are many other experiments that animals are not do not need all samples to generalize.
I was saying maybe incorrectly the other thing, that this was what you were doing with the monkey. That's why it was important to show the monkey only like 3 or 4 different rotations of the paperclip so that you didn't augment the monkey's data set too much.
But this is exhaustive augmentation versus like a subsample augmentation. Let's call it this way. And what people try to do these days is exhaustive augmentation or somehow auto-augmentation. And we have a paper with Edgar Dobribon and Evangelos and Stefanos on how to choose transformations on the fly so that depending on the task, so that we achieve this. It's called the transformational risk minimization.
Empirically, what's do people know how many transformations you have to add to the data set so that the performance can be acceptable?
That's a very good point, except, I mean, the performance, I mean, it's very difficult to talk about performance these days in terms of training. I mean, these guys from NLP, they're using 400 billion. If you add, you multiply by 10, everything, I mean, I don't know what it really will mean. The main idea is to really just hard code it into the network. And the triumph of equivariance is really the AlphaFold 2. This is the protein structure prediction system from DeepMind, in addition to Dan Spielman, who received the breakthrough prize last week, also the Savis, and he's, I don't know how many people, there was at least one more from DeepMind. All the authors? Yeah.
No, only 2 of the authors.
Only 2 of the authors, yeah. And what happens with let me explain briefly about the AlphaFold 2, and there is a very nice blog by Fabian Fuchs here, which explains that. So in protein prediction, you have these amino acids. You have the alpha atom, that's why for alpha fold, and you have the N and the C, and you have about between 300 and 400 of them concatenated in a way which is like concatenation of rigid triangles connected with a CN connection. And in the past, in order to achieve like invariance in this prediction, people would choose invariant variables like the angles between every amino acid. But this was extremely sensitive in general, mathematically, to choose like pretty much like Euler angles as a rotation representation. And as soon as deep learning came in, people started predicting directly the XYZ positions of the atoms. But in order to define XYZ, you really need a frame of reference. This is like a gauge problem in physics. And your network has to be like invariant to this gauge of this frame of reference. And it is impossible to do really augmentation over all possible translations and rotations in the inputs in order to achieve this equivalence, because you would have to sample the whole rigid motion group, both the translation and the rotation. And that's why they have built what is called an SE3 transformer, and I will explain briefly at the end how we applied also in one of our papers. And it's not really the equivariance which really made the breakthrough in the prediction. It's really the more like the transformer, but making the transformer also equivariant was the main success actually of equivariance itself. It is very interesting to that's it's Fabian Fuchs. If you Google it, it's the blog description of the AlphaFold is very interesting, because in particular for everybody in geometry who predicts XYZ coordinates. So we differentiate between equivariance by design versus equivariance by augmentation. And in equivariance by design, we really have much lower sample complexity. We really have, we don't augment with respect to this information. And correspondingly, we need fewer parameters. And we achieve, like by guaranteed better generalization with respect to these transformations. And I will mainly present results on three-dimensional vision. First on retrieval, and then on reconstruction. So in retrieval or shape classification, you really want to, you have as an input a three-dimensional shape captured either from a database or from depth sensors, and you want to either find the closest, like retrieval, or just classify it. And then we have also sparse, such I will show the problem of sparse point clouds, for which you need a continuous surface reconstruction. Let me start with a very simple example, our first result at ICLR 18 on how to achieve equivariance, and this is how it was done in the 90s, before deep learning. So this is equivariance to the set of similarities and rotations, the SIM2 group, which means if you just scale and rotate like n-mist, for example, inputs. And the idea is what if we can take the rotation and the scale and we can convert it to a translation transformation just by changing the coordinates of an image, right? And there is a, I mean, the differential geometric idea behind that is that if you have a group and you have exponential maps, instead of multiplying really the whole like matrices under specific conditions, you could really just add the exponents. So you would get really a shift there. And there was a theorem based on differential geometry, like about the canonical, all the canonical coordinates theorem by Segman and Zivi from Technion, which proved that for any abelian Lie group, there is a change of coordinates under which the action becomes a translation. And as a matter of fact, there is an additional constraint that the Lie generators of the group has to be linearly independent. So one example of this transform is like the log polar transform. The log polar transform is if you the log polar transform is if you take pretty much if you convert first to polar coordinates like in complex numbers, and then you take the logarithm of the radius, you get something like this where the rotational angle is here and here is the logarithm of the scale. And if you multiply inside the logarithm, you add. So this is a translation. If you rotate, you add an angle. So this is a translation as well. So if I convert to coordinates, which is like the angle and the log, any scaling and rotation can be a translation. So I can apply anything I know about translational convolutions and achieve the same thing.
Yeah, that could be a naive question. But so I can see why translation and variance is often a good thing, but it also seems to be like throwing away important information, like, you know, text recognition application, you know, like E is kind of a rotation of a 3, and then 8 is a rotation of an infinity sign.
Oh yeah. I mean, this is not really the translation. This is really on the. This is there are tasks where you don't want the rotation, like 180 degrees. Okay. I will not present this paper. We have a special paper where we recognize, depending on the task, what kind of groups we have to be equivariant. This is together with that W1. Here it is for the full rotation. It's not naive. It's very good point. And so in this case, we can see that by taking the log polar transform, we can deal with scaling and rotations. But the problem is that the log polar transform changes depending on where I put the center, right? Because I have always to compute the, so I have a point x, y, I have the radius, so I really need to compute the distance from the center and then take the log of this. Okay. So this is a very usual problem in equivariance when you cannot achieve equivariance with respect to the whole group, which in this case would be not only scaling and rotation, but also the translation. Where is the object? So and in this case, we apply something which is called a spatial transformer. This was before the attention is all you need paper, the transformer in the geometric sense, not in the attention sense. This is a former paper where the pose of every the subgroup, which in this case is the translation, is learned. So here the network learns the center of the 8, and after it learns the center of the 8, it applies the log polar transform with respect to this center, and then applies the classification. This is a quite dirty trick. Okay. There is a generalization for that. I mean, in the capsule networks that Jeff Hinton has proposed, every capsule really computes, for example, the example
You say the center is there for every data point or
For every data point separately, yeah.
so you predict the center and
You predict the center and then apply the log polar transform. Everything is differentiable throughout. So, so it is really a little of cheating here, right? It is because we don't have a full, we don't have a translational convolution. We have only the scalar rotation convolution.
And when you're training the center predictor, you need an augmented data set in which you.
No, we only have a class labels. And you get like feature maps for the number 3. If the number 3 is rotated, they are shifted in the angle direction. You see here the shift, and if it is a scale, they are shifted to the right. And obviously, this was, I mean, in MNIST, we have done experiment only in MNIST on that. And in MNIST, you cannot really show any, the error is already very low. So this is on a test on something called Sim2 MNIST. There is also Road to MNIST, where the testing data set is only scale, actually rotation and scalings, and you train only on the basic data set, and you test on the augmented, and this is on SVHN, which is the Street View, actually science. So we don't want to live with dirty tricks. I mean, this was a disaster if for every group. We have to choose a subgroup and learn something. So the main question we asked, and not only us, but like Taco Cohen, the University of Amsterdam, and Max Welling, and Rizzi Condor at the University of Chicago, and few other groups. It was in 2017 and 18. Is if we replace a convolution the way we know it here, like this is the definition of the convolution, with a general thing called a group convolution, where instead of like translating here, you would take just the group action view, and you would integrate, instead of integrating over translation, you would integrate over the group action.
measure over the group.
So I will not go into that. Yeah, you have to deal with a measure. Actually, Jean Gallet is writing now, actually, based on this discussion we had started, he's writing a harmonic analysis book. And this is for the groups we are dealing with. We have a Cauchy measure, which is for the rotation, just sine theta, d theta, and for the 3D, yeah, it is. So these are the main thing in this picture is that this is rotated copies, that is transformed copies of the kernel. So the same way you take a kernel and you shift it, the main idea of the group convolution is you're going to take a kernel and not only shift it, but also rotate it and scale it or rotate it in 3D. So that's the main idea. The question is if it is easy to translate something in 2D, but it's not really easy to rotate a kernel like in 3D rotations, and also how you can discretize that. So the first paper here, it was by Taco Cohen and Max Welling in 2016. They started just with a discrete rotation, like with 90 degrees. And I will present an example here with another discrete rotation. And the main reason I start with a discrete group is first, I will not have to deal with the measure. I will do a simple summation. And second, I will not have a discretization issue about where really to take the samples of the transformed copies. And I start with a finite subgroup of the 3D rotations, which is the icosahedral group, which is known from crystallography in chemistry and has 60 elements. So you see where actually this particular edge goes in all these 60 rotations. And we applied this to recognition of objects from multiple views, where the way to do that is to model an object as forget the monkey and the brain. We have an input, the full 3D here, and the equivariance is really not just the few views. It's really that if every face, if we take a polyhedral representation of, like if we take like a dome around the object, and every camera here gets just one view. And this becomes my representation of an object, like a series of 2D views. How this recognition problem based on this vector is invariant at the end, and in between in the layer is equivariant to the orientation of the object. Okay.
So the input here is like a set of three-dimensional coordinates, like each say like binary. Like, is there something?
Yeah, the input here is can be, but this particular case is a couple, and it can be a dense point cloud. I shouldn't say forget the monkeys. Actually, if I take each of these views, this vector can be actually representing one viewpoint and one neuron. And this was started from several groups, and what they were doing in order to achieve invariance would be what we call invariance by pooling. They would just choose if you would run a regular network, a 2D network like a ResNet on each of those views. You get like, let's say 512 vectors. You would choose for every channel the maximum value. So you would do what we call view pooling. And this view pooling gives an approximate invariance with respect to the views. So you would get one vector, and then you would run it through a classifier. So this is really approximate invariance, like a lot of other pooling operations, like average pooling brings you usually an invariance. And what we really wanted to do is to get rid of this pooling and apply like a true equivariance here, having this notion of finite group convolutions with rotated copies. There were several representations. We went back to like the regular, what they call the so-called Platonic polyhedra, and there were several representations for the views, and there is a difference here between the representation of your domain, of the function of the features you have, in terms of how many elements it has, and the rotational group, which is fixed, and in this case, it has 60 elements. And to make things simple, I will present only one of those polyhedrons, which has 60 faces, as many as the elements of the finite group. So that every actually rotation just becomes a permutation of the faces of this polyhedron with the 60 views. So, and this is like one of those permutations. When the inside this dome, the airplane is like rotating, then you get a permutation action on the set of views. And so if we then compute, we take every view, we compute like a 512 vector feature for for each of those phases. And then we apply here these are the rotated copies, like when you rotate the polyhedron, and we apply just the convolution operation of the rotations, not translations. And outside is just a summation over the channels. This is sorry, this is a normalization, and this is a nonlinear Verello that we apply on top. And what is that? No, this is just a visualization. Instead of showing the permutation, how the features, if the features are the colors, how the features are changing when the inside the dome, the airplane is changing. And what we have shown here is that if we train only on rotations, which are like pretty much the airplane on the runway, like rotations around the vertical axis, and we test on the full SO3 set, then we achieve about the same performance as the multiple view network, but with 12 times fewer parameters. And we definitely beat like other networks like the point net and the volumetric approaches. The reason we still trained on a subset of the rotations is because if we present only one view, then really the other networks do not do well at all. So it's not fair to the other networks.
So I guess like you really want rotation and variance over like the sphere, but that's tricky. So you pick sort of this discretization, this like platonic solid that has 60 something sides. I guess you could have picked a platonic solid that has like 600 something sides or 6,000 something sides.
I don't think they exist.
Or no.
I think that's the maximum.
That's the next. Okay, maybe that answers my question.
I mean,
that
that's a really regular.
and you pick that one, so that's the biggest.
Yeah.
But you could have picked a smaller one. Do you know what? My question was going to be, do you know how various things scale?
Yeah, it's very funny because I gave the same talk in Athens, and Christopher Papadimitriou interrupted me for 15 minutes to explain to all the students the regular equation. And we can do it. This was outside in. We can do it inside out, where imagine that you just have one of these like an array of cameras looking to the outside, and you want to classify the scene, for example, like kitchen versus bedroom, and this is how ours performs. Again, the same pipeline for every view. We get the ResNet vector, and we apply the finite rotations. Obviously, to answer Aaron's question, how do we deal with more continuous rotations? And this is really the main bulk of Carlos's and Christine's PhDs. Carlos has also, I really recommend you to read his WP2, which is also on the archive and cited quite well on just the theory of it without a single experiment. And the yeah.
So what's the theoretical guarantee that you have on the training?
The theoretical guarantee here is this, that you have in this CAD, like in the 3D shapes. The theoretical guarantee on the finite is that if it is really exactly on the finite rotation, then you can have exactly the same classification labels. If it is in between, you don't know. I mean, it performs really well, as you saw.
Right.
It's not really you don't know, but the exact guarantee is only on this finite rotation.
Is there a way to measure robustness to this positional imprecision?
There are papers, yeah, there are papers for robustness, not for the finite rotation, for the one that I'm going to show here.
Is it difficult to generalize this to a constrained set of the group?
Yes. That's mathematically impossible because it's not a group anymore. So if you constrain to minus 30 degrees, it's not a group. So that's the problem. Unless finitely you can design something which will be a group. You can find equivalences of rotations for any Z, like one-dimensional things like Z5, Z7, or any. You can construct. I would say you can construct finite versions of that. It has to be a closed. For the convolution to work, there should be a closed operation, closed action. And yes.
So in the case of the iconicity, what is the length of time? So you have the group is acting on the group.
Oh, the lambda priority is because it's acting on the 512. It's acting on the channels.
What is that?
Oh no, it's again a warping operator. That's the yeah. It's a permutation in this case. Yeah, it's always in the finite case, always a permutation. Yeah, it's a permutation matrix. It's very easy. Now let us assume that the representation is not multiple views, but for example, I can take taking dense multiple views will not scale up because for every view we run a resonance. So you would need you would really explode your network. But let us have a representation of the 3D object, which is, for example, the value is a vector, and it has the distances from the center. If you take out from the center where it intersects, and this can really represent the object on the sphere. And the question is how then to apply a full, like pretty much continuous equivariance to the to a spherical function, which is still like a scalar valued. Even what we say here scalar valued is really that even if you have a vector of channels, each of them is independent, so it doesn't have to rotate as a tangent vector. About the same time, this was ICLR 18, and our papers was CCCV 2018. There came these two Tacos and our spherical networks. By the way, Tacos got also the best paper at ICLR. When following the Aaron's like discretization suggestion, if you have a latitude and longitude, the problem with running a kernel on the sphere is that it is really while it is really on the sphere, it is it support is rotational invariant. Here it support itself it's not, and you would really need a lookup table if you want every time to apply this as a kernel to a function defined on latitude and longitude. So for this, in general, we need different representations for these lambdas, okay? And for our for the action of the group on the signal. So the main, I don't have it in any slide, but the main idea is that if you have the usual like W like as a layer and on the output of the channels, and then you apply some nonlinearity. So let's say this is like a linear layer. Then we want that if what we had before is this. Okay, and so that if you warp the input and you run it through the layer, then that is the same as running the origin through the layer and then warping the input. Now, because the representations of this W might not be, the type of the W might not be all the same. It may be a scalar, it may be a vector, it may be a matrix. And or a higher like a tensor. What we really want with respect to this particular warping function lambda is to find the warping function as like a representation of the group and satisfy this equation, where this is the input representation and this is the output representation. And this can be different if the type, if for example you have input scalars and output you have a vector. So for example, for 2D rotations, so a representation of a group is to map the group onto a vector space. So every action that you have is the matrix multiplication. Very simple, you know that from the for the two-dimensional rotations. And there is actually Jean Gallier explains it very well on his notes. His notes are available. That for general, like for compact groups, there is a theorem which says that first that if you can have a Fourier transform, and that the basis of the Fourier transform are such group representations. For example, for a one-dimensional rotation, here we have just the harmonic exponential, and more general, in this case, the Fourier coefficients, because the representations are matrices here, they are not a complex number, they are complex matrices. The Fourier coefficients are also matrices. Why we need the Fourier coefficients is because all this, the discretization problem is actually outsourced to the Fourier transform. Instead of discretizing in latitude and longitude and trying to have a lookup table on applying a kernel, we take the Fourier transform and then we have a pointwise multiplication. And then all the burden of the discretization is on how you compute the Fourier transform to the specific group. And this gives you also some flexibility. For example, when you take the Fourier transform, there is a Fourier transform for discretization of latitude and longitude, for example, from David Rockmore at Dartmouth, and which runs for the sphere, it runs in n squared log n. And then when you operate on the Fourier transform, you can even cut like high frequency coefficients, and you have the flexibility also on do very simple like filtering without touching the original signal. In any case, the key here is to avoid all these like 600 like elements that Aaron mentioned, and any discretization of the latitude and longitude, you can transfer all the burden to the Fourier. Yes.
But the sphere is not a group.
Yeah, exactly. So I will go into that. Of course, the sphere is not a group. So the sphere is what is called a homogeneous space of a group. So the sphere is a homogeneous space of SO3. And this is like a space where the group acts transitively, which means if I want to go from one place on the sphere to the other, I cannot add, as we know, at least the people in robotics here, I cannot add Euler angles. Okay, if you want to go from one place on the earth to the other, I have to apply a full rotation. And so this is like space is like the sphere where the group action is transitive, which means you arrive again on the original space. They're called homogeneous spaces. And usually a lot of these homogeneous spaces are what we call quotient. So the sphere is SO3 modulo SO2, which is really this modulo SO2 is, if you stand on the Earth, is the two-dimensional rotation around yourself. So if you exclude this, you get only the longitude and the latitude. And there is a particular property of Fourier transforms on groups and the corresponding homogeneous properties. These are like frequencies in 2 dimensions, L and M, and N. So we have 3 Euler angles. We have 3 frequencies in rotation, but they don't correspond one-to-one. And the main property of the Fourier series on the sphere and other homogeneous spaces is that they are sparse. And this is what you can exploit in order not only to make the pointwise multiplications very efficient, but also to design very good kernels. And my student, I will skip through this. So my student Yinshuang Zhu, together with Jacques Lay, she actually generalized this from the sphere to the plane and the 3D volume, which are also homogeneous spaces if you write them as general rigid transformation modulo the rotations. And by exploiting this sparsity, we showed that you can really have a unifying, like a recipe on how to design kernels and how also to design nonlinearities. Yes.
Let's say your second affiliation.
Yeah. What?
Departments.
Yeah. I'm not sure. Why the twist? Should be only Penn. Anyway, so to visualize what is happening, every layer, actually, we achieve that every layer, if we take just one channel and visualize it, these are multiple channels, every layer is rotating exactly the way that the input is rotating. If at the end we take the average, then we can construct a vector which is almost, as you see, invariant to the input. Almost invariant, and this is because of the actual discretization used for the Fourier transform. So the same almost you have for rotations in between the finite rotations. Here you have it because of the discretization itself of the Fourier, which is though much denser. Now, to answer the homogeneous space question, there are 2 ways to do this. One is like Taco Cohen and others, where they lift everything on SO3 from the beginning. And this is also what Yinshuang does. And you do everything in SO3 and project it down. And our original paper, where everything is a spherical convolution, which means every layer, the result is on the sphere and not on SO3. And these are the results of hours when it is trained on vertical rotations and tested in general. And this is the difference in the number of parameters of the competing network. It has 100 million versus 500 million. Now, this is nothing with respect to current transformers, but for convolutional networks, it is still a big actual improvement. And this is the number of actually fixes we use in the discretization, which is also their effect is linear on the speed. 10 more minutes would be okay. We started at 12. So one more. So this is for things you can apply a convolution. But as you said, who applies convolution these days, right? Everybody is applying transformers. And indeed, also there are problems where you cannot apply convolution, like a set. So the AlphaFold problem is a set of atoms. You cannot apply convolution on the AlphaFold. So imagine that you have a point cloud, and while doing the classification, it worked quite well with mapping it on the sphere. If you want to do the convolution, if you want to do a reconstruction, and from the sparse point cloud to get a surface, then convolution will not work, because you will not get expressive features that are really expressive in the really sparse neighborhood of the point cloud. And this is our most recent results, which is submitted now today to ICLR. And I think I'm going to give a different talk about this. But let me just give you the essence of this is just the following, that if you train networks on objects, purely objects, and then you go into a scene and take depth views, and you have this as an input. If you want to do a reconstruction without recognizing which are the objects, in order for the objects to be reconstructed with the right orientation, this network has to be equivariant. Oh, thank you. Okay, ignore. All right. So, yeah, I don't have time to go over the occupancy network, but I want to show the network, which is this one. So we use, this is the input is the point cloud, and output is what we call an occupancy field, which is if you input a query feature XYZ, if you're going to find its occupancy value 0 for outside and 1 for inside. And the question here, which is the main question also in the AlphaFold, is in the main attention mechanism, where you have the basic multiplication of the query with the key. How can you do this equivariant with respect to a full 3D motion, like both translations and notations? And the way you do it equivariant with respect to the translation is by taking local operations and taking only the difference. This makes it equivariant. It makes it invariant, not invariant, to the reference coordinate systems. And the second is to apply this actually guarantee to the K and D matrices of the attention. And we do exactly the same on the decoder part, where with the only things that we don't transform are the queries. This is based just on pure algebra if you apply the attention formula. So what will happen here is that if an object, if we have an input as an object, we take one feature vector per point, and to reconstruct the value of one possible specific point, we take the neighborhood of the query point. And that's if you don't apply equivariance, like in the occupancy net or the vector neurons or the convolutional occupancy net, these are the results. And these are the results. This is the result with this input. If you have an equivariant network like ours, and this is on a bigger scene where you reconstruct correctly, like the whole chairs around the tables with the correct orientations and other objects, where you have trained only on every object separately. I think so. You can do a lot with group convolutions. Now, what is the drawback of this, right? The drawback is that you need in your group somebody like Yin Shuang to do all the computations if you invent a new group. And this is not something that you can take off the shelf. As soon though as the covariance networks, equivariant like networks become like libraries, and there is one called the E3NN, the tensor field network. I think people will start using them more extensively, and right now they use them extensively more in chemistry rather than in computer vision. I presented very basic ways on how to enforce equivariance through group convolutions and how to do it with an attention. And I didn't go deep into how does this work onto like not scalar fields, but vector fields and more general tensor fields. I think I'm going to stop here.